A quadratic function is a polynomial function of degree 2 which produces a parabola when graphed. Let's start with the simplest quadratic function. F of x equals x squared. As x moves away from 0 in either direction, the output grows rapidly, giving us this classical U-shaped parabola. Let's consider the quadratic function of two variables by adding y squared to get fxy equals x squared plus y squared. We transition from a 2D curve to a perfectly symmetric ball-shaped surface in 3D. Looking at this function from directly above, the level curves, where the function equals a constant, establish perfect circles. This symmetry reflects the equal weighting of x and y. Before going further, let's recall the standard equation of an ellipse. The parameters a and b control the width and height along each axis. For example, if we set a equals 1 and b equals 3, the ellipse stretches 3 times further along the y-axis than it does along the x-axis. Similarly, the equation 9x squared plus y squared equals 9 defines an ellipse. The coefficient 9 on the x term effectively compresses the shape horizontally, while the function extends to 3 units vertically. When x and y terms have different coefficients, the level curves are no longer circles. They become ellipses stretched along the y direction. In 3D, this asymmetry creates a clear visual. The surface rises much more steeply along the x-axis than the y-axis, resulting in an elliptical ball. Adding a cross term for xy introduces a multiplication between x and y. We can write this compactly as a W transpose AW, where A is a 2 by 2 symmetry matrix. The eigenvalue decomposition of A reveals its hidden structure. We can compute the eigenvalues and eigenvectors with just a few lines of NumPy. The two eigenvalues are approximately line pointer 47 and 0.53, and the eigenvectors tell us the principal directions of the function. Using the eigenvalue decomposition, we can rewrite the quadratic form as a weighted sum of squared projections onto the eigenvectors. This decouples the two directions entirely. Setting the function f equal to 1 gives us an ellipse equation in the eigenvector coordinate system. The semi-axes are 1 over square root of lambda 1 and 1 over square root of lambda 2. The eigenvectors u1 and u2 define the orientation of the ellipse. Notice they are perpendicular, an important property of symmetric matrices. The eigenvalues scale the axis. Since lambda 1 is large, the ellipse is compressed along u1. Since lambda 2 is small, it's stretched along u2. Here's a full picture. The ellipse oriented along the eigenvectors, with the axis lengths controlled by the inverse square roots of the eigenvalues. Setting the function f equal to lambda 1 times lambda 2 gives a different ellipse. So the rows of eigenvalues have been changed. The semi-axis become square root of lambda 2 and the square root of lambda 1. This ellipse is larger but shares the same orientation defined by the eigenvectors. The geometry is fully determined by the matrix A. Here we see the axis length square root of lambda 2 along u1 and the square root of lambda 1 along u2. The larger eigenvalue stretches a perpendicular direction. Finally, the level curve line x squared plus 4xy plus y squared equals 5 produces this tilted ellipse, rotated in the plane because of the cross term in the original function. The contour plot confirms it. Our level curves are tilted ellipses, rotated according to the eigenvectors of the matrix A. In 3D, it's no longer aligned with the coordinate axis, but the eigenvalue decomposition lets us fully understand its geometry. To summarize, without a cross term, the contours are axis-aligned ellipses and the 3D surface is a symmetric ball. With a cross term, everything rotates, but by using eigenvalue decomposition, we see that the underlying mass remains elegant, organized, and deeply interpretable. Thanks for watching this video. Feel free to reach out.